fyrsta morgunfundi brunahönnun Íslands. Í dag þá erum við gest á verkís hjá Guigay. Það er alltaf fylgja verkefni sem hann var við skipulagningu á skipulagningu og undirbúning við verðarmótum í Guigay sem var hundi í Lóðarsafnuna fyrir okkur síðan. Þannig að gjörðu svo gjörðs.
Ďakujem. Meneer spreek Georges Guigay. Ja, dokter Silvia Vatmir, FAKIS. Ja, Atlas Ronske. So my discussion today will be about fire and crowd evacuation modeling in the low-ceiling sport arena. That I wrote with very small. Actually, I gave this lecture a few weeks ago in a conference called Fire and Evacuation Modeling Technical Conference. That was held in Washington, or near Washington, in September. I will just show you the internet site. So this conference, it was held by a company called Sunderhead Engineering, about building software, and SFP. And so you can see with a list of lectures. Probably some of you will recognize kynnir, one of the biggest guys in the fire safety engineering business. He's the one who is actually developing FDS, leading the group in FDS. So we have a lot of lectures from people from LIST and other engineering companies. So for now, you can download these presentations, but you have to pay for it. But in a few months, I think in April 2015, it will be free of charge, so you will have lectures, videos, and articles. So it was very interesting. A lot of, we could say, big people, a lot to learn from them, and I learned actually a lot from this conference. There were about 200 participants from many countries, two from Iceland, David from FSI, and I, but that made Iceland one of the biggest delegation, not the delegation in this conference. There were 26 presentations, so many case studies, some verification, validation, and research. Also, it was really on what we call performance-based design. That is using softwares like smoke simulation softwares or evacuation softwares to design a building or to check if it's fire safe or not and how to improve the building, as opposed to prescriptive methods that is just following the code like looking at the gas and going through all these rules. So performance-based design allows us to have a much bigger and fancier building maybe. But two things about this software. Today I will present both FDS, that is Fire Dynamics Simulator, and Pathfinder, but what we have to remember is that they are maybe the most advanced tools that we can get now, but they are only tools. That's extremely important. And nothing will replace, at least for the moment, good engineering sense and also fire safety expertise. And that was quite funny. Just at the conference, there was a reception, and I was just starting to relax a bit. And suddenly I saw both Kevin McBratton and one guy called Daniel Svensson, who is the head of Sunderhead Engineering, coming right to me. So I was prepared for an argument about this only tools thing. I thought they would be quite unhappy with it, but actually I was very surprised. They completely agreed with me, and instead of an argument, we ended up with a good drink and a discussion. It was nice. So yes, engineering sense is still, even they admitted that they were always the only tools, and engineering sense is still needed. One thing also that is quite important to bear in mind is that these softwares are very complex. Sometimes some people manage to have some fancy results with a nice picture, we could say, but it needs a lot of experience to use them. I've been using them for 16 years now, and I still have to learn quite often. And I've seen so many times while teaching at university or engineering companies, some wrong models or things that are very strange. I saw once a model with I didn't know what the fire was. And I cleaned, I saw some smoke. And the fire was somewhere just below the ceiling, just floating on the air. It was very strange. So some people, they just don't know the softwares. They just rush for it, do some click and clicking things, and things are right. You have to bear in mind, it's very powerful, but it can be also very dangerous to use it. Don't know what you're doing. Okay, that was introduction about influence in the lectures. Now, okay, this was the subject of this study. It was a few days ago, sorry, it was 2 weeks ago, it was a European Team Gym Championship in Reykjavik. Now, I don't know how it went in a gymmy kind of way, how Iceland did in this competition. But I know that at least there was no fire, which is good for me. No, it was quite a big competition. It was 4 days, up to 1,000 participants from 20 countries. And organizers, they wanted to have 4,200 spectators, roughly. Okay, the thing is, at this time, there is no indoor stadium that was directly suitable for this event. So for a stadium, for example, here you can see all there, that's not all. It's too small. There are some sitting stands, but it's too small. It's about 2,500, and the floor competition for itself is too small. Then there are some other stadiums, like football stadiums, but they don't have sitting stands. So the solution that was accepted was to use here athletics and exhibition hall. That is a new extension from Paraset, and to put some temporary sitting stands. But of course, this is completely different from the original configuration. It was just training, small competitions. It could be exhibition or a concert, but no sitting stands. So we need a completely new fire risk assessment. So this is why the fire brigade and organizers came to us at Vakis, and actually Vakis did this job for free as a sponsorship to the competition. I think we were gold sponsors or something. Oh, the fire safety problem. This is the hall here. So it's about 5,000 square meters. The ceiling height is between 8.3 and 11 meters. The walls right here, sorry. Here this is concrete, and then we have a steel roof. You can see you have some 7 blowers, mechanical vents. I think they extract 50 cubic meters per second, so very powerful vents. And you have 18 different doors for evacuation. Very good evacuation doors. We have some and all along this wall. So evacuation conditions are very good in case, for example, of a flood concert or something. But in this case, of course, it's completely different. The problem is to have people getting down at these stages. So you can see here all the evacuation routes, and this is what the architect from Architeo and a company called Total Event Solution, who are actually renting the seats. It's quite a big company, I think. They were involved in the London Olympics. So they sent me first this first layout and asked me what I thought. I asked him first about, did he look at evacuation? And he said, yes, I looked at British standards for number of seats, low, so it was okay with standards. And he took these very simple NFP equations that are very suitable for a room like this. In my opinion, they are not suitable for this stadium. If you look at it more on the design. So in the south stage, which is actually this one. So all the evacuation. Doors, you have competition floor. And what the first problem I saw immediately is that the access to the competition floor. You see, here it's a very narrow passage. It's supposed only to be for athletes to come in, perform, and then go out the other way. But there are no other way out to the competition floor to outside. And that was my first problem because, okay, if you are this little guy here, and it means you are sitting somewhere here or here, so it's about 4.5 meters, this floor. So your head is maybe 2.5 meters below the ceiling. And in such a wide space with a lot of people all around, it can be very stressful, especially you will see the smoke going down very quickly. So for me, it's a perfect case, this closing building. There's a lot of people, very narrow passages. It's a perfect case for panic. And if just someone trapped on the floor, we'll get some panic. So I wanted some people are supposed to go, for example, this way. I'll take this turn and then this one. But we all know that many people, especially the one on front row, they will try to go this way, especially if there is panic. So I wanted to make sure that people could evacuate from the ground floor, competition floor, to avoid this panic scene. So, but anyway, what was sure, it was too complex case to say just with some NFPA model, very simple NFPA model. It was too simple to say it's okay. So we went into a much deeper investigation. So first, I had to find out the time before the little guy completely has to evacuate. And for this, I used fire and smoke modeling with FDS, Fire Dynamic Simulator. So what my domain, it was 100 times 75, 50 meters. Doors open after 120 seconds, 20 square meters of air intake, 7 blowers. Actually, I tested many meshes. The mesh resolution is more or less the precision of the calculation. And okay, the smaller your grid is, the best your resolution is supposed to be. But of course, it takes much more power and much longer to perform these calculations. And I wanted to see the different results with a very coarse mesh, 1 meter, and a shorter one that was 50. And also, when I joined Dakis about 1 year ago, I got this very fancy computer that's a personal computer with 16 processors and very powerful, so I wanted to test and see how far I could go. So this is why I went down to 25 centimeters and gave me about 7 million cells. So I could actually set, I could go down and have a huge calculation, still having some reasonable computational time. So design fire, you can see here is a fire, it's a 10 megawatt. My filter is 10 meter visibility at 2 meters above floor. And actually, if you look at this picture here, sorry. Okay, this is a 3D model of the stadium. Okay, you can see here in green very few doors. And all these blowers. But of course I have to consider what if these blowers don't start, which can always happen. So every scenario that I simulated was simulated in 2 cases, with blowers functioning and not functioning. To be absolutely sure it will be okay. Here you can see I cut the model, so the fire, I put it in the middle of the competition floor, and you can see the circumstance. So as I said, I wanted, this is maybe a bit technical, but I wanted to see how sensitive it was to the mesh. For both the old version of FDS5 and the new version of FDS6. It is also why, because I was part of, before FDS6 was released, I was part of the FDS6 beta testers, which was a group of maybe 20 specialists worldwide who were testing the software before being released. So I wanted to test as part of this project, FDS5 against FDS6. So first, mesh sensitivity. Okay, in this table we are, this is normal condition when the blowers are working fine, and I'm testing both FDS5 and 6 with 100 centimeters and 50 centimeters resolution. So what I got is that the layer 8, which is the 8 where the hot layer stops, it stabilizes. You can see it here. This is a layer 8 for every 4 cases. So in dotted line it's FDS5 and in pale line it's FDS6. So you can see first that for the first 150 seconds there's no hot layer formation. There's still not enough smoke for the enough temperature difference. And then suddenly the job done when this hot layer goes down. And what you could say that it's stabilized about 1.1 to 1.5, which is higher with the final mesh. So final mesh gave you some better results somehow. That was what we are expecting. And also having about 1 meter difference between meshes. It's very important in this case because of this low ceiling, the ray is standing 2.5 meters below the ceiling, so 1 meter precision is huge. So it was absolutely essential to go down at least to these 50 meters. Then about FDS5 versus FDS6, I could see that generally the layer 8 was lower with FDS6. So FDS6 is actually reacting a little bit sooner. This is FDS6, and there's something like 60 seconds. So layer 8 is going down before this case, so it's more reactive somehow. Now I cannot say at this time that FDS6 is better than FDS5. There's always a question, why do you use this new software? Is it better? I couldn't answer. I guess it's better. I want to find out if it was better, and we all agreed it was. But from this research, I could only see that FDS6 was more conservative. I think that with FDS6, one problem is that the CPU is actually double. So instead of having 1 day of calculation, you have 2 days. So this is why you need to know why you are using this FDS6. Now I'll just show you a few results. Okay, this is my fire, and these are my temperature vectors. So the red one, I think it's the computer. Here the temperature at 120 degrees, and you can see here the smoke. And here you have formation of layer 8, so with temperature between 80 and 120 degrees. You can see that very slowly it will go down. In this case, with the blowers, it didn't go down so quickly. And in this position, it's a position of someone who's standing at the top of the IO stand. Now, if we look at this, is just to look at how the blowers work. So once again, you have the fire here, and then you will see that the blowers are very efficient. This is visibility, so it's the depth of smoke. So you can see that the blowers are extremely efficient in venting all the smoke. Okay, in this snapshot you can see exactly what my little guy at the top of the stairs will see when the smoke goes down, so it can be very stressful. And also it's interesting for us to see what we want to get from the software. It's not only fancy. We want to see visibility. And in this cise, this is the visibility 2 meters above my little guy. No, sorry, his seat, so it's his head is smallest. He's got his head. But what we want is standing actually at this point. And we want him to evacuate before, if you look at this visibility, the black and the yellow part means visibility below 10 meters. And we don't want him to face these conditions. But he must evacuate before this happens. You can see here that he's standing here. So you can see that he will be submitted to smoke. And this is before, if the blowers work, it's before, let's say, 11 minutes. No, sorry, if it's, yes, 11 minutes if it works, and about 9 minutes if the blowers don't work. So I want people to evacuate this upper stance before this 520 seconds. That's my objective at this time. What we call a critical time. And A is called for adverse conditions, which means blowers not working. That's FDS6, and those 25 centimeters mesh is very precise mesh. So now that I have this critical time, so this is what FDS or smoke simulation gives me. Now I have to look at evacuation. My little humans will react. And for this I use software called Pathfinder. It's a 3D software for evacuation. And this is actually my model here in south stage, north stage, and the lower stages. And in total I have about 3,936 occupants here in this table. And you can see it's very similar to the first model that was sent to me by Akiteo. Only for a few details, I think it's quite representative. What was very important was to keep the width of passages and how it was and what was the density of people. This is what really mattered, and the position of stairs. It doesn't really matter if, for example, if this angle here is not exactly the same as this one. We don't really care. We just want, for example, this stairway to be as wide as this one. This is a short video just to show you the model. So this is the position of occupants before it starts. So this is a more general view. My occupants they start to move about 2 minutes after the fire started. This is what we call detection and reaction time. Actually, people always, okay, here comes the fire signal. It's a few seconds, and people just look at themselves. Okay, is the first alarm? Then is the first alarm? Where is my purse? Where is everything? It always takes at least 2 minutes for people to start reacting. Then once one of them goes, and everybody goes at the same time. So this simulation here, it starts actually about 2 minutes and 30 seconds in the simulation, because I wanted to shorten it so you can see people, groups of people gathering close to the stairs. And okay, some people are lucky you can enter directly into the stairway. But you can see that all the people that are on the top, they have to wait for the people who are on the row below to enter the stairs and to evacuate before they can themselves get into the stairs. So you have this one bottleneck of people completely at the top. And this is the main point. We need to have these people evacuate. The video stopped. I don't know why. You see. And you can see also that some of the people, they try to go, if this is blocked, they try to look for alternative routes. But in my simulation, they cannot go through the competition floor. and they cannot jump to the next seats. So we can say there are some restrictions. In real life, people will try to jump to the next seats instead of queuing. So somehow it's a conservative calculation. If you look into details, the graph on the right part is actually the number of occupants on these 3 rows here, completely at the top of the third stage. I wanted to see how long it took to evacuate and to be down, at least not to be at this top. Okay, first we have about 200 occupants on these stages. As you can see on the graph, and there are these 2 minutes about here, so nobody moved, of course, and just a bit before, about 100 seconds, a few people start to move and to evacuate. And then during the first seconds, a lot of people manage to get into the stairs. But then the stairs are completely full. Now they have to wait for people to go down before they can go down themselves. And this is where they need to wait. And it takes them about 3 minutes to come into this situation. And it's quite free in front of them. So then evacuation is very efficient. So we had this a few days ago. These 2 to 3 minutes waiting, it seems to be a bit long, this part. But I was in a football game about 2 weeks ago. I was completely downstage, so I also had to wait for people to move before I could move. And it takes, I think, much more than 2 minutes for me to be able to start just moving. So that's not so this seems quite realistic. And okay, evacuation of this IS rows was completed after 442 seconds. And the complete evacuation of all, once they evacuated the stand, of course, is very quick. So it was about 480 seconds. So what this model shows me is that the layout is fine if everything goes as intended. And that's how it gets tricky, because it never goes as intended. You always have some people that they don't want to move, they want to go the other way, maybe their kid is sitting somewhere else. And what I really was afraid of was panic. And so what I told them first, this is the modification we made from this original layout. So first of all, okay, we said we want 3 evacuation routes from the competition floor. So there is one here, one over there, and then at this corner. What is especially important is that each of these evacuation routes is directly in front of exit routes. So this will be very efficient to come in directly out. It's also the case at the top. So now people are able to evacuate from the competition floor. And also we wanted to keep a passage here, at least 1.4 meters wide, to create an alternative route. So now the people, instead of waiting to come in here, they will be able to walk on this way and out here. So this was, I think, the main improvement.